Well, welcome to Air Science. Let's go through this practice test. I'll try to make it as quick as I can. So here we go. This is the Tectonics practice test. It's in your Google Classroom. Check it out. The cross-section of the Earth below shows a P wave moving away from an earthquake epicenter. In other words, the earthquake occurred here on a cutout of the whole planet, to seismic station A. Seismic stations are places where they detect earthquakes. No S waves arrive at seismic A because, and this theme I'd say is definitely going to appear, it's a pretty straightforward, kind of almost trivia question. And it's choice one. Some parts of the core are liquid. It doesn't specifically say that in this reference table. I mean, if you have yours printed and you want to write liquid right here, not a terrible idea. Or if you're clever, you might note that this is the place where the temperature is above the melting points. Therefore, it's a liquid. Therefore, no S waves go through. That's been in a couple of these videos. I would anticipate seeing that one. I'll try to make this test as easy as I can, folks, but that'll be one of them. So if you did all your Google Earth work the other day, or you watched the videos of me playing with Google Earth, here is East African Rift Valley and some spreading through the Red Sea here. And let's see what they ask. What appears to be happening to the cross-hatched region of Eastern Africa? This section over here is headed that way. That was my thumb. I'll do it with a pen. It's heading that way. So what do we got? Folded mountain range. That would be when things come together. That's a no. Several volcanic mountains are forming as the rest of Africa subducts. Subduction is when things come together, so that's a no. This region is moving eastward relative to the rest of Africa, I like. And moving northward is a no. So we're looking at choice 3 there. These deals with ridges, I really did it quick, just so you guys saw it like in the middle of the Atlantic Ocean. And I said we did a lab, we would have done a lab in class, but along the ocean, developing ocean floor right here, or if we could go that way and go over to the Atlantic Ocean, to the mid-ocean ridge, the idea is that there's a ridge, and then on either side, because it's spreading like two conveyor belts going away from the ridge, there's a symmetry. The whole point of the difficult lab we would have done, the answers to like 4 of the questions on that lab are just symmetry, 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 symmetry. So whenever you get a question like this, you're looking for symmetry. That's dead wrong. And it's this whole idea that there's polarity reversals, and I didn't talk about it. We're not going to bug you with it, but there's things that happen with Earth's magnetic field that, because this is basalt and it's got iron in it, it's a mafic igneous rock, there's things within that iron that are altered by Earth's magnetic field at the time that the rock formed. And you don't really need to know that. I'm not gonna bust your chops about that. But the pattern must be symmetrical. So I'm looking choice 1 there. There's a symmetry on either side of the ridge as it spreads out. Where's my fingers? As it spreads out. Bump, 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 bump. That's that. Moving on. All right, this one was kind of a scale model of the inside of the Earth at 0 kilometers depth. In other words, the surface is right there, down to the very center. So the MOHO. Now the MOHO defines the difference between the crust and the mantle. Don't worry about memorizing it. It's sitting right here in your reference tables. MOHO, which is the Mohorovic discontinuity. Don't need to know that either. Separates that black line and that white line. And this, if you've been watching the videos this week, like I've mentioned that this is a great reference table for all the deep stuff, but the surface stuff, it's just a little bit tricky to tell what's going on. But it says that this black line here is crust, this white line here is rigid mantle. So that's that. We need to be between the crust and the mantle. Or really, if you come over here, this number is going to be really difficult to read. It's going to be so close to the surface. Hopefully our choices hook us up a little bit. And they do. So we're very, very close to the surface. It's going to be letter A. Up towards the top. All right, what's next? What is the approximate thickness of zone C? That's just a classic, can you like use a scale here? So what do we got? These look like they go by 200s. So I'm going to say it's about 2, 4, 6, 8, 10, 12, 14, 16, 18-ish hundred thick. There you go on 16. You could also do it by subtracting if that's at about 800 and that's at about 2900. just do a little bit of quick arithmetic. But 16 is going to be your answer there. I think these other ones are too big. Unless I screwed up my math there. Leave a comment if I did. Which zone is characterized by partially melted rock and large-scale convection currents? They show us that's a convection cell right there. That's another convection cell. And I mentioned in one of the other videos that there's a slightly antiquated idea that convection within the cystinosphere is what drives plate motion. It really is the idea of subduction. They call this slab pull. It pulls down on the plate, and that is more responsible for it, or ridges can like push. But anyway, what we're going to look for is basically that's the convection cell. It's in the astenosphere. Which one of those is the astenosphere? I'm going B. B. Which zone of Earth's interior has a density closest to the densities of the other terrestrial planets? Yeah, I remember this one. So, that's kind of a making you go back to the past, blast from the past. If you got to go to another reference table. If you remember this guy from way back in the beginning of the year. And you would have to remember what the terrestrial planets are. The terrestrial planets are the first four. The Jovian planets are the last four. So we're going to be looking for densities like in the, about 4 to about 5, somewhere in there. So that's what we want. Now we go back to this guy. And I'm liking the mantle for this one. So what are they going to want from us here? A, C. I'm not thinking A. I'm liking C. And E and D are too deep. Going down into the core, your densities get to be pretty darn high. So that's going to be a no-go. So I'm liking C. Which will be choice 3. S waves produced by an earthquake are transmitted through zones, blah, 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 blah. Again, here it is. Like, it's going to show up in one form or another. The outer core is a liquid. Give me the outer core on that thing, and you got it. Now, I guess the one kind of trick to this is, like, they would go through the inner core if they made it, but they can't make it to the inner core because the outer core surrounds it. So, I'm thinking 2 is your best go there. Not zones D and E. Yeah. S waves can't go through the liquid outer core. Why don't I pause there, do it another video in just a moment, just so I don't have to do too long of an upload here. Welcome to Earth Science. We'll see you in a second. We'll see if we can find Ducky. Oh, that's Ducky. I'll see if we can find Bunny.